Chemistry, Unit 3, Chapter 7. Okay. Factors affecting rate of reaction. In this session, we will be investigating what are some of the factors that we could change so as to change the rate of chemical reaction. In the previous session, we already discussed that we could use a catalyst. Now, what are the things that we can do? So, reaction happens when there is successful collision. Okay? So in order to speed up a reaction, we could potentially increase the proportion of successful collisions that have energy that is equal to or greater than the activation energy by, for example, using a catalyst. Right? So here we're talking about increasing the proportion of successful collisions when we use catalyst. That means that the overall amount of collisions per unit time remains the same. But out of them, more percentage of that collision is now successful. So can we maybe also increase the overall amount of collisions within the unit time? Yes, we can. That is, if we could increase the frequency of successful collisions by increasing the overall amount of collisions that could occur in a given time. So it's kind of like for the first option, we're increasing the numerator of this fraction, and then for the second operation, we could also make the percentage the same, but if we can increase the overall amount of collisions, then there's more chance of having successful collisions within that same period of time. So comparing these two, if we are to use the human analogy, the first one is kind of like you go on to the same amount of dates, but then somehow something clicks and then you just meet more people that are suitable for you. But that's not likely to happen for human beings, right? Like the percentage is most likely to be the same. So in order to find the right one, you probably need to go out more often. So by increasing the amount of dates, you are increasing the chance, aka frequency for particles, to find the right one. Now, rate increases as frequency of successful collision increases. So when we say frequency, we're talking about the amount of collisions within the same period of time. Okay. So for gaseous reactants, to do that, we can increase pressure. For reactions that happen in solutions, we can increase concentration of reactants. And for solid reactants, we can increase surface area, okay, by breaking them down to smaller particles. So let's look at surface area. For example, if we put magnesium solid into an acidic solution, it will react and produce hydrogen gas. So if our magnesium particle, represented here in green, if the particle is large, okay, you can see that only the atoms on the surface can be in contact, can be in collision with the hydrogen cations around it. So all those atoms in the center of the lump remains intact. So they cannot have collisions at all. Okay? So increase the surface area, then by breaking it down, you can see that we increase the surface area of this entire lump by breaking it down. So now almost all atoms of magnesium metal can be in contact and therefore having collisions with hydrogen cations. And so the frequency of collisions between the solid and the other reactants increases. Yeah? So when you have big solid, the atoms within the solid is not participating in the reaction until the surface atoms have reacted. But by breaking it down, all the atoms can have collision and potentially lead to successful collision. Concentration for solutions or pressure for gas, they somehow work in similar ways. Okay? So how does this look like is if you potentially have this much of like particles. If this is a solution, by increasing the concentration, you make sure the overall volume of the container or of the solution remains the same, but you just add more particles. Okay? And if it's a gaseous product, we can reduce the volume of the gas container and therefore also increase the amount of gas particles within that volume. Okay, so we're still increasing the concentration of gas particles, but the representation is that we have increased the pressure of gas. Okay, you can see that both will give reactant particles less space to move around, and therefore they collide into each other more often. So this then will increase the frequency of collisions between reactant molecules. And if more collisions occur per unit time, then more successful collisions will also occur, and therefore rate of reaction will increase. Temperature. So what does temperature do? Okay, so increasing temperature of reactants will directly increase the kinetic energy of reacting particles. And kinetic energy transfers into the speed of movement by this equation. So if you increase the kinetic energy of your reactant particles, then the particles will move around faster. Okay, so you can see that if the particles are moving around faster, then they're more likely to collide into each other within a given amount of time, and therefore higher frequency of successful collision will be the result. At the same time, if we increase the kinetic energy of particles, we're basically increasing the energy in particles, right? That also means that more particles will have energy that's more than the activation energy required. And therefore, if we increase temperature, we have also increased the proportion of successful collisions by increasing the energy of the particles. And therefore, again, result in more successful collisions within the same amount of time. So temperature acts in both ways, right? Both the amount of overall collision and the proportion of successful collisions. Now, how do we represent change in temperature in Maxwell-Boltzmann distribution? Because temperature has changed the energy of the particles, right? So once there's energy of particles, we can represent it on Maxwell-Boltzmann distribution curve. So let's think about, you have the same amount of particles, but now since you have increased their energy, it's still the same amount. So the area under the curve should remain the same. But now you should have more particles that are actually more particles in the higher range of energy. Okay, so initially when you have an increased temperature, you have this much of particles that's above activation energy. But when you have increased temperature, you have less particles at lower energy and more particles at higher energy. And therefore, since activation energy remains the same, then you will have more particles at a higher energy range, and therefore higher proportion of successful collisions will happen. Okay? So increasing temperature will result in higher proportion of particles with sufficient energy to have successful collisions. How do we represent rate of reaction on a graph? Okay. So rate of reaction can be determined by using how much a reactant is being used up, or how much of a product is formed in a given period of time. So your graph could be increasing or decreasing based on which one do you choose to use. Okay. So the graph can either be plotted using amount of reactants versus time, or amount of products versus time. Or sometimes the amount is actually represented in concentration, volume, or mass. So let's look at this. So calcium carbonate reacting with hydrochloric acid. The blue line is when we use larger particles. You can see the y-axis is the volume of carbon dioxide. That's what they choose to represent the rate of reaction. And the x-axis is always time. So when we use larger particles, it takes this amount of time to complete this reaction. But when we switch to smaller particles, then the curve becomes steeper and the reaction has completed within a much shorter period of time. Okay? So the gradient represents the rate of reaction. Another example can be found here. You have hydrogen and iodine to produce hydrogen iodide. Okay, so here the red line represents the reactants being consumed. Yeah, so when you use reactants, your line will be going down. But something that's more interesting here, you probably notice that the gradient of the curve is the rate of reaction, right? But the gradient of the curve is changing over time as well. The curve is getting flatter and flatter, yeah? Okay, so as you can see that actually gives you an idea. As the reaction proceeds, the rate of reaction decreases because the concentration of reactants decreases. Yeah? Let's summarize. Now, what are the factors that affect rate of reactions? Surface area of solid reactants, concentration of reactants in a solution, gas pressure, temperature, or the presence of catalyst, which we talked about in previous sessions. So those marked in blue, they increase the frequency of successful collisions alone, okay? And those marked in red, they increase the proportion of successful collisions. And temperature, which is marked in purple, act in both ways.